when people talk about labeled data, they mean not only the picture, but also the class for it. So people worry about AI taking away jobs. It is actually making a new underclass of people. The crowdsourcing Amazon MTurk people, who will be shown these pictures and say, tell me what's in it. And they'll give a label. And that's how actually labeled data is generated. And there is actually a company called Crowdflower, which is doing extremely well. All it does is for your particular company, it tries to make labeled data. That is what you will wind up doing for a while before machines take over and you don't even know how to do that. Okay? But the point is, if those labels are costly, you don't want to pay Crowdflower for this. Is there something I can do to use this information? I'll tell you a crazy idea. You have this stuff, right? Learn an I-based classifier. You did that. Now, because you have an I-based classifier, you can predict the class for all of these. In fact, you can predict the class posterior for all of these. For example, I might say this particular one is will weight 0.70, won't weight, not will weight 0.20. That's what, let's say, your learned Naive classifier told you. So you can do this for all these unlabeled examples. Do you agree? Up until this, everything is fine. But now I want you to understand that I just gave you answers for these unlabeled guys. You just gave it. So this example happens to be a fractional example of yes with 0.708 and fractional example of no with 0.308. So in fact, instead of having just 12 examples, now I have 24 examples where each of these examples can be actually fractional yeses and fractional nos. One of the advantages of going through grade school and going beyond that is you know how to do ratios even if there are decimals on the numerator and the denominator. You don't just always have to say 7 by 12. You can say what is 7.32 by 4.97. And that won't be a problem. 7.32 by 10.97. You see what I'm saying? So now I'm going to ask you the following question. Now that you have more examples, why don't you recompute the Naive classifier? Okay, so he says doesn't change it. How many people think that might actually work? If it works, won't it be so cool? It looks like sort of you are, Martin Luther King said, pull yourself by your bootstraps. We found those somehow. So essentially, I learned the parameters on this. Then I using those parameters, I predicted the missing values here. Now that I have the entire data, I'm going to say I have more data and I will recompute the parameters. I won't stop there. I will re-estimate the labels and I'll keep doing until something magical happens. If he is right, accuracy shouldn't change. Right? That's what happens. So what this is showing is, this is you saying, don't give me any unlabeled example. I have no use for them. And this is your friend saying, give me your unlabeled examples. I will sort of do this crazy loopy thing, which is I will learn from the part of the data, I'll predict the rest of the data, and I'll keep doing this cycle. Does that blow your mind? I mean, it's blowing your mind that how long this semester has been going on, but this will also blow your mind. If you can do this, you are able to learn from unlabeled data. This, by the way, my friends, is called semi-supervised learning. Semi-supervised learning. Imagine the amount of stuff that gets open now. You no longer need complete data. You can do partial data and you complete it yourself. So you indeed are kind of pulling yourself by your bootstraps. Okay? So this is actually what I just saying you should do. Okay? You learn an I-based classifier C0 using the few items for which we have labels. Use C0 to predict the ratings for the rest of the items. Then we go into this loop. Learn the classifier C1 using all the ratings, real as well as predicted. I said ratings because it can also be used for recommendation systems. Recommendation systems are just supervised learning. So instead of wherever I said ratings, just predict the class rating. Okay? And then use C1 to re-predict the ratings for all the unknown items until no change in ratings happens. Then you say, this is what I have learned from this rating. And you will be ready. And what you actually wound up doing in this particular case, it turns out, is you are learning Bayes nets from incomplete data. Because this part is incomplete. If you just think of it as unlabeled, you think the only thing that can be missing is the label. But if you just think of it as incomplete, any part of this can be missing and you will be able to use those examples. And I told you earlier on that Bayes networks with incomplete data is a harder problem and that you have to do EM. You just did EM. This is what expectation maximization algorithm is. Okay? So the part about expectation and maximization, when you compute the parameters, you are maximizing the likelihood using MLE. And then having computed the parameters, you are expecting the values for this. Having expected the values, you re-maximize for the parameters. Expectation, maximization, innovation. Now, the reason it works, so basically you have the E step, and this works basically, even though I showed it to you in the context of unlabeled examples, it works for any incomplete data. It actually works when there is, the entire data has no class. So in fact, if you are, imagine even this has no class. I only have Russell just hanging around at the restaurant. And I get sick of it and I leave. So I never know whether he actually waited or not. You understand what I'm saying? This idea still works. And that's like, forget about pulling up your bootstraps. You don't even have boots. You still can pull yourself. The reason is exactly the same. It's the same theory that works. It's an incomplete data. It turns out this is a variable whose value you don't know. Okay? And I'll show you this without actually. So you basically are doing this E step where you compute. So in that example, if you don't know the classes, in the beginning you just randomly assign classes. Or actually start with random parameterization for the network. And then using the parameters, compute the labels. They could be fractional labels. Using the labels, recompute the parameters. You will get something. And if this, so basically, when you are doing the M step, you are computing the parameters. When you are doing E step, you are doing Bayes net inference. This works for any arbitrary Bayes network. The big ones, the small ones, the I-Bayes classifiers, everything. This is why you will keep hearing, if you hang around enough time in AI, you keep hearing about expectation maximization algorithm. And whenever you hear EM, you are supposed to show some respect because it actually looks like magic, but it has theory. And what is the theory? Oh, by the way, so it turns out that in this particular example, this is actually from the textbook. I won't have time to go through this step by step, but in the second example, we have this issue of wrappers and the wrappers, the bags in which different kinds of candies are put. and you don't quite know what the distribution on the bag says. If you don't know the distribution, it will still be able to learn the distribution. That's sort of like, if you think bag is the label, I just didn't give you the bag value at all, and you'll still be able to do it. And two more things before I go to the math part. This winds up being useful in all sorts of places. Many of you have heard, and you will continue to hear about hidden Markov models. In hidden Markov models, essentially it's a network, a Bayes network, where you will only be giving the observation variables. You will never be giving the state variables in the training data. So you only keep seeing, in this example, you are stuck in this classroom, things are changing outside, you keep seeing random people coming in, some come with umbrellas, some don't come with umbrellas, and you're trying to guess whether it's raining on that day or not raining on that day. And the same thing, I'm talking, some phonemes are falling on your ears, and you're trying to figure out what the heck is Rob trying to say. Speech recognition is originally done with hidden Markov models. Rabiner actually used hidden Markov models, and then it becomes, they're just special cases of Bayes networks. In fact, these things are called dynamic Bayes networks because they are going forward in time. Now the interesting thing is, since I don't know these values at all, the training data will always be just in terms of the observations, and you're still supposed to learn the entire network. And this one is called Baum-Welsh algorithm. For hidden Markov models. It does EM. Okay, this stuff is more interesting. Read this. I won't show you that, but I want to show you just a little piece of why EM works. For those of you who are interested, can go back to this slide. The basic idea is that the log likelihood will now involve summation. So within the log, you have to sum over missing variables. Because what you see is an example which doesn't give values to some of the variables. So the probability that you would see that example is essentially the probability of seeing this example with label equal to yes plus with label equal to no. So you have to sum both of them. So essentially the log likelihood winds up having a sum inside. That throws a huge big spanner into the works of doing nice derivatives and equating them to zero. Furthermore, this log likelihood function would be more like this. It's non-convex. So really, the way to do this would be to do gradient ascent. So you will take, at any given point, you take the gradient and make a step in the direction of the gradient. What EM does essentially is it allows you to compute a simpler distribution, which winds up being equal to this distribution at this point. And then you can find its maximum analytically. And then it turns out its maximum, if you go to that its maximum, that would be a nice big step in the right direction. Because remember, you're trying to get here. But by doing this, you make this big step. That's what EM does. So EM is a very customized gradient ascent algorithm. Okay? And it does much better in many cases. But it's really underneath it all, it's just a customized Bayes network, gradient ascent algorithm. Okay? So that sort of ends, that sort of ends the discussion on the learning with Bayes networks. And we talked about Bayesian learning, we talked about how to approximate it with map and MLE. And then we did MLE for known topology, we did MLE for unknown topology, where you can't just do MLE, you have to bring in a penalty term to say that complex topology should not be picked unless there is a very good reason. And then we did incomplete data. Incomplete data brings in EM, it just blows your mind in terms of how much you can do. Because now all of a sudden, you don't even need labels. Many people talk about this idea called unsupervised learning. Unsupervised learning means essentially there is no class information, there is no supervision. Here is an answer. Okay? So I will stop that part here. I'm going to spend 10 more minutes, if I may, on trying to complete the So, next 10 minutes is the careful goodbye for me and relieved escape for you. Some of you already had the gumption to run away before, but the rest of you are stuck in this 10 minutes. Okay, so sort of an obligatory summary of what happened in this course. We started with this idea, although you came for neural networks, that's all you wanted to learn, nothing else. I tried to convince you that really what AI is trying to do is make intelligent agents. And learning is but a small part of it. It's important but small. In particular, an agent requires the ability to have models and reason with them. Reasoning essentially involves search. So you, for example, look at search, planning. We didn't actually do planning, but we did MDPs. We did inference, which is logical resolution as well as basic inference. We looked at representation mechanisms, representing things as logic, representing things as numerical functions, such as neural networks, representing things as probabilities. We also looked at learning models. Although you only cared about neural networks, we looked at lots and lots of other interesting learning algorithms, including nowadays, which is the reason you get to keep your job. You get to get your job by talking about convolutional networks and the cloud from home, but then if you actually try to use them for most jobs you'll get into, they are not just using image data. They will actually wind up having hand-coded features and UDPs, other stuff. They're much more efficient. So keep that in mind. If you look at the crazy big textbook that I forced you to buy, the stuff in green is what we wound up actually covering in a non-trivial amount of fashion. No chapter is completely covered, but it's been covered more if it's in green. If the stuff is in brown, then I sort of gave it some passing references during the semester. If it is in red, we haven't done it, so you should do it if you want. That's the parts that are missing from there. To the extent textbook is AI complete, those are the things. In fact, we went a lot more than the textbook when we came to things like neural networks. Because as you can say, the third edition of Russell has all of 2.7 pages of neural networks, and we spent 3 classes. Okay. And you, of course, just read only about that. Okay. So, making a class that's going to torture you actually requires work. Okay. It's much, much, much easier to do an easy class. You would be happy, I would be happy instead of doing so on at this point of time. But thankfully, to make it hard, I had great help. Okay, and of course, Prashant is here, and there are undergrad TAs, Marios and John. Are they here right now? No. And then of course, Andrew. And those guys really are the ones you should thank for making your life miserable. I was just here keeping the jokes. Okay. So if they weren't there, I would have had exams, I would have had projects, I would have had homeworks. You would just come or not come, and you would have had fun. Seriously, those are the guys that you should be at. Also, when I teach my courses, not only my entire lab is involved, one way or other, and so the rest of them, for example, you are grading, as well as whenever I make exams, I kind of show it to my lab guinea pigs so that they'll see whether or not it's going to kill you guys or not kill you guys. And so they wind up taking part in it. So for example, Anagha was here, as well as Shailik, and then Sharath, who was actually the last year's TA. They all looked at the exams, including the ones that we are about to see after the end of this class, and so they were also very helpful. And Lydia actually has done some nice graphics that we'll be showing you. That's the Piazza contribution stuff. Okay, So obviously, a large number of people who have written stuff. So for example, people like Amit and where's Cody Dana? There are some of these names I kept seeing in, for example, student summaries, because I keep sending these random noisy emails that you guys completely ignore, saying this is a place where you can write student summaries. Only a couple of suckers would do it. Amit is one, and Cody is the other, and a few others. I think Jaharsh, who is not shown up here, he was also kind of very nice. So, these are all the numbers that they have done. And if you look at, for example, the instructor side, you can see, for example, Andrew viewed 345 posts and gave 126 contributions. Prashant viewed 334, 102, and of course, undergraduate TAs also spent a lot of time. I had no other life, so I was just mostly watching videos. So, that brings us to the post reflections. Or, I would like to call it 11 questions that lead to love. How many of you know 36 questions that lead to love? See, some of you have goals in life. So, essentially, this is sort of thinking about what happened in the course so that maybe you like it, okay? And I'm happy to say that I had great fun reading most of your summaries. I was up until 11:59 yesterday, then I had to sleep so that I can actually wake up now. And I know that some of you have posted after that. I'm going to still read them. Several of the ones that were posted, I read all of them for sure. And then some of them I also commented. So you might see what I might have written. So I will also tell you to look at when you get chance, maybe after the exam, look at what other students got out of this. So if they're getting something out and you're not getting, you're getting gypped. So you should do also to get that. Okay? So you might want to look at it. So here is the summary. This actually, after I went to sleep, Ilya stayed awake and looked at the entire set of answers that you have provided, and she made these word clouds. You see, we have no other life. By the way, before I completely forgot, I'm very, very sorry to do this. Sriram, the guy is not taking the course. Without him, you would have been actually forced to come to the class. No. So all of you bozos who showed up only today and are surprised that, oh, these are the classroom looks, thank him, because he was actually sitting here for every class, recording every class. So thank you, Sriram. At least I from my side, and I think the other bozos should be here. So that's another thanks. But anyways, the 5 ideas you appreciated. These are some of the things that came up. I want to just make some brief comments. So obviously, exploration came up a lot, Pacman came up a lot, pruning came up a lot, alpha beta. Lots of people found it interesting. People did sort of. It kind of gives you which words occurred more often in the first part of the. So you may want to look at it. The second one is 3 non-trivial technical details, and that of course neural networks came up, functions and gradient descent, again alphabetical pruning, policy, overfitting came up a lot, of course gradient came up. So you can see what sort of topics very important. Okay? No Republicans, Democrats, for example. 2 ideas that transcended the course. Many of you, actually the language is big because many of you are struck by the Nicaraguan deaf children language. Interesting, you should look at more of that video, that's nice. And then of course, many of you thought about the exploration versus exploitation trade-off that you deal with in your own lives and how that is connected. And that's exactly the point. So I once said to somebody who was interviewing me about AI and teaching, I said, it requires a particularly bad teacher to make AI uninteresting. Okay, because it's just a fascinating subject. So I hope I'm not that bad that I still make that subject uninteresting. And it looks like we got a lot from this. The last thing, one topic that you wished covered. Neural network. So I want to give you one of the last of my crazy examples. Before I go forward with this, there are 2 more slides after this. So many years back, I went to an Indian classical dance performance. Now, you will be wondering, why the heck would you be talking about it? But you by now know that anything can come after anything in this class. So I went to this Indian dance, classical dance performance with a friend of mine who is herself a very good dancer. And then during the dance, I was seeing it, and then I told my friend, this girl, she's dancing really. My friend looked at me and said, stop kidding yourself, you bozo, she's pretty. That's what you're looking at. A really good dancer is that person there. Okay? So stop kidding yourself. My point, the reason I brought this up is we are human. There's nothing wrong in being interested in doing neural networks because that's where the jobs are. But don't delude yourself into thinking that's the only vast topic in this course. Some people actually have written neural networks, I wish we have done more of it because it's a really vast topic. That's like me saying, that pretty girl, my God, she's dancing so well. In respect of the fact that she's not actually a good dancer. So it's important, as I said, to understand what you're doing and do introspection. Every topic we did in this course is vast. And every one of them will wind up being useful in your life. Do read up more neural networks and get all those jobs, and all the power to you. And more of the jobs to you, the less for the bozos. But don't kid yourself that that's the only thing that's what you do. There's a lot more. And I hope that you got that out of yourselves. Now, of course, those of you who read the 50 and 36 questions to fall in love know that there's supposed to be some staring at the end of the 36 questions. So I was going to set up time so each of you can come and stare at me, but no. So instead, you get to stare for the next several days at the take home. This is the front page of the take home. And you get to stare at it, and you will fall in love all over again. So the last slide. Bye-bye to you with Schindler's List. So that's the last end of the movie dialogue. And so my version of the dialogue is like this. But basically the topics that I wanted to cover and did not have enough time to cover. That's the thing that I actually do. That's what I do. If you read the chapter 11 of the textbook and look at the end of the textbook, you see that most of the stuff in that textbook and that chapter comes from the work that we have done in our lab. So that's what we have done. So we are actually the textbook. I'm much more interested in human-aware AI. I tried to talk about that, but I will spend more time on that. Bold is about multiple agents. In fact, human-aware AI is the first of it. You wind up having to deal with humans. That's an extra agent. And so you have to model it. I would like to do a lot more about multi-agent stuff. Some people actually ask for it. Handling partial observability is extremely important. Everything that people are doing assumes full observability. Not because it's the way the world works, but because it's an easier problem to solve. Dealing with partial observability will bring you, for example, things like DBs, HMMs, all these fun things, and it typically doesn't get done. There are some classical topics like CSP and structural properties of constraint graphs that I would have liked to do, and in the mind, there are one lectures that you can look at. Of course, maybe I would have been less demanding more often, but we'll look at it. So, if I can stop this. Marvin Minsky, remember how many people remember Marvin Minsky? Really? Okay, Marvin Minsky is one of the 4 people who are considered the founding fathers of AI. He died actually last year. And in fact, we started in the IJCAI International Joint Conference on AI, we started this thing called Minsky Medal, which the first Minsky Medal was given to AlphaGo this year. Okay? So Marvin Minsky has said, one of the things he said, with understanding comes a sense of loss. That's just natural. You know, when you understand why something works, the magic is done. The magic is done, you feel, oh, this can't be AI. You know, I know how to do it, so it can't be AI. Okay? However, magic can't be learned. The only thing you can learn is removing the magic. And so I really hope that during this semester, you do experience a sense of loss. Not just the sleep and social life, but also the technical aspect. Okay? Thank you all for your time, and it was great teaching you. We'll see you.